Now we're going to go through the review problems for your exam. Number 1, a school guidance counselor examines how many extracurricular activities students participate in and their grade point average. The guidance counselor says, the evidence indicates that the correlation between the number of extracurricular activities a student participates in and his or her grade point average is close to 0. Which of the following is the most important appropriate conclusion? So first of all, if you have a correlation of close to 0, that means there is practically no relationship between the number of extracurricular activities and a student's grade. So students involved tend to be with poor grades. No, we're saying no relationship. No conclusion should be made based on the correlation without looking at a scatter plot. Well, unless the correlation is 0 and we can say, it does not appear to be a relationship. Now, there might be a nonlinear relationship, but it's not indicating a linear relationship. Students with good grades tend to be students who are not involved. Who knows? This has nothing to do with it. Students involved in many extracurricular activities are just as likely to get good grades as bad grades. I would agree with that because there's no correlation. Students with good grades tend to be students who are involved in many extracurricular activities. E would imply a correlation, so I'm going to go back to the choice D. D is the correct one. They're just as likely to get good grades as bad. There does not seem to be a relationship between the number of extracurricular activities and their grade. Number 2, an AP statistics student designs an experiment to see whether today's high school students are becoming too calculator dependent. She prepares 2 quizzes, both of which contain 40 questions that are best done using paper and pencil methods. A random sample of 30 students participates in the experiment. Each student takes both quizzes, one with a calculator and one without, in a random order. To analyze the data, the students construct a scatter plot that displays a linear association between the number of correct answers with and without a calculator for the 30 students. A least squares regression yields the equation calculator score, predicted calculator score, is negative 1.2 plus 0.865 times the pencil score, with a correlation of 0.79. Which of the following statements is or are true? Number 1, if the student had used a calculator as the explanatory variable, the correlation would remain the same. That is true. That is true. So correlation doesn't change when you switch the explanatory and response variables. And you could argue that calculator can be explanatory. If we know how you score with a calculator, we're pretty good. We know that you're going to score higher than that with a pencil, or we're pretty sure based on the model. Number 2, if the student had used calculator as the explanatory variable, the slope of the least squares line would be the same. Well, in this case, the slope would be positive. It's a positive relationship, but it doesn't mean it's going to be 0.865. Slope almost always changes when you swap variables. Number 3, the standard deviation of the number of correct answers on the paper and pencil quizzes was smaller than the standard deviation on the calculator quizzes. So there is a relationship. What do we know here? We know R, we know the slope. Well, there happens to be a formula on your math chart that relates a slope with correlation with standard deviation for y and x. So we're going to go ahead and substitute in both our slope and our correlation. Now I'm going to divide both sides by 0.79. Now hopefully you can see that the standard deviation for a calculator has to be bigger than the standard deviation for pencil because this number is going to be greater than 1. All right. You can also say the standard deviation for a pencil will be less than that for a calculator. Now, don't think that that's the standard deviation. It's just the ratio of these two is the same as that ratio. The standard deviations could be greater than 1 for all we know. Remember, this is a correlation that can be never bigger than 1. And this is your slope. So those are not the actual standard deviation. So please don't confuse those. So this tells us that 3 is a correct statement. and 1 is a correct statement. So 1 and 3. Problems 3 through 5. Scientists examined the activity level of 7 fish at different temperatures. Fish activity was rated on a scale of 0, no activity, to 100, maximal activity. The temperature was measured in degrees Celsius. A computer regression printout and a residual plot are provided. So this is the residual plot. Notice that the horizontal axis on the residual plot is labeled fitted value, which means the same thing as predicted value. So, first of all, they ask, what is the correlation between temperature and fish activity? Well, first of all, we don't get correlation on the computer printout. It gives us R² and R² adjusted. Now, we do not do this one. This is when you have multi-variables going on, more than the 2. So like if we did temperature and who knows what else. Magnetic field, I don't know. All right, or amount of food they ate. So we ignore this one. We don't use that one at all. But R², that is the one we use. So correlation is R. We need to take square root R² and then check the sign. So taking the square root of this, always change it to a decimal. We get 0.95. Now I have plus or minus to remind me that I need to double check what the sign should be. Well, the sign is related to the slope, so here's the R², which we have, and let me go ahead and highlight right here. This is the slope right there, okay? The slope is negative, so that means that the correlation has to be negative, so our answer is B. Number 4, what was the actual activity level rating for the fish at a temperature of 20 degrees Celsius? So we're going to go ahead and calculate predicted, which remember is the fitted value. So predicted is going to be, well, I have to create the model, which means I need to look at the slope. Remember we said this was the slope last time. This is your y-intercept or your constant, all right? So we're going to create an equation with that. And here's our equation. At predicted activity, when you have that hat on it, it says predicted, equals your y-intercept. And in this case, because the slope is negative, we say minus 3.2167 times the temp. And we substitute in the temp, and we get the predicted activity is 84.286. Well, if we go to that point, so it's slightly before 85, right? It's this point. So this tells me the residual. What's the residual? Well, first of all, this value is approximately 3. But there is a formula for residual, which is actual minus predicted. The way you can remember which way to subtract is you're in AP class. A comes before P. Actual minus predicted. So I'm going to substitute in for the residual and the predicted. Since I know those values, predicted is 84.286 and the residual is 3. And then solving for actual, we get 87.3. So we're guessing that it was, and again, remember, I estimated that at 3. I don't know if it was exactly 3. And we get 87 is closest to this value. Number 5, which of the following gives a correct interpretation of S in this setting? So S is over here. And here's a definition for S. If you don't have this on your cheat sheet, you might want to write this down. It's the typical distance between the actual and predicted values using the least squares regression line. So here, this is talking about slope, right? And actually, it would be wrong because it's predicted to decrease, right? So activity should be, for every 1% increase in temperature, 1 degree increase, fish activity is predicted to increase. No, it's actually predicted to decrease. And not by this amount, it's predicted to decrease by that amount, 3.2167, whatever that gauge is. It is not the typical distance of temperature readings. That would be the standard deviation for that. It's not the typical distance of activity level readings. That would be the standard deviation of Y. So this is the standard deviation of X, standard deviation of Y. Neither one of these is S. At a temperature of 0 degrees, this model predicts an activity level of 4.785. That's actually your constant, your y-intercept. It would be 148.62. What it does do, it is the typical distance of the activity level ratings of the actual activity level ratings from the least squares line, okay? Number 6, which of the following statements is not true of the correlation R between the length in inches and the weights in pounds of a sample of brook trout? So, R would not change if we measured the lengths of trout. So first of all, we're looking for not true, all right? And I'm going to look at an A and B at the same time. It's nice to remember that R is without units. It's not impacted by the units of measurement. So both A and B are true. But we're looking for not trues. C, R must be a value between -1 and 1. Yes, that's true. Check the activity we did on the F1 day with the produce types and incomes, and we said R has to be between -1 and 1 inclusive. D is false. R is without units. It's not measured in inches, all right? And then E is true. If longer trout tend to also be heavier than R, the correlation is positive. That would mean a positive slope, and that as length increases, so does the weight, and this would be true if longer trout also tend to be heavier, which kind of makes sense, actually. So our correct answer, in a way, our not true answer is D. Number 7, the scatter plot shows a relationship between the number of people per television set and the number of people per physician for 40 countries, along with the least squares regression line. In Ethiopia, there were 503 people per TV and 36,660 people per doctor. A scatter plot shows a relationship between people per TV and people per doctor. The marking on the horizontal axis labeled people per TV starts from 0 and ends at 600, with equal increments of 100, and the marking on the vertical axis labeled people per doctor starts from 0 and ends at 40,000, with equal increments of 5,000. An upward slanting line is shown from the point 0, which extends up to the point 17,500 on the vertical axis. The dots do not follow a pattern and are distributed randomly. The cluster of dots is denser between the points of 0 to 100 on the horizontal axis, which correspond to the points 0 to 12,500 on the vertical axis. So there's your 0 to 12,500, and there's your 0 to 100. Which of the following is correct? Is the correlation greater than 1? No, correlation is never, never, never greater than 1. A is false. Okay, here's for B. Ethiopia has more people per doctor than expected based on how many people it has per TV. Well, we looked at 530. There's the dot for Ethiopia. This is predicted based on our model. Yeah, it's definitely higher than predicted. So the actual is higher than predicted. Increasing the number of TVs in a country will attract more doctors. Well, although we have this graph as the explanatory variable, that does not guarantee causation. There's probably a confounding variable that would create this relationship, although it's not a strong relationship, so it must not be a very good confounding variable. So, could be that money, how rich the country is confounding. So, correlation does not equal causation. All right. And then finally, D, the slope of the least squares regression line is less than 1. No, it's pretty high. It's going up like thousands of units. You could actually see where it tells you where they start and stop. 0 to, here it goes to like 20,000 from 0 over 650. That's definitely greater than 1. So the correlation is less than 1, but the slope is greater than 1. The point for Ethiopia is decreasing the slope of the least squares regression line. Actually, this point is pulling the line up. If it weren't there, it might be going like this. So it's increasing the slope. So that doesn't match. The only statement that's true is B. The actual is higher than predicted. Number 8, when we standardize the values of a variable, the distribution of standardized values has mean 0 and standard deviation 1. Remember that. That is 100% true. Remember when we do our normal distribution, and we do the standardized model, we put in 0 for the mean and 1 for the standard deviation. Now suppose we measure two variables, x and y, on each of several subjects. We standardize both variables and then compute the least squares regression line. Suppose the slope of the least squares regression line is negative 0.44. We may conclude either something about the intercept or the correlation. So first of all, let's go back to that formula that we had. You will encounter this formula. Well, we know b is the slope. It's negative 0.44. We don't know r, but we do know that x and y are standardized, so our standard deviations are 1. So I'm going to substitute in negative 0.44, 1, and 1, which tells me, oh, once I multiply that out, oh, r equals negative 0.44. The correlation is negative 0.44. Number 9, there is a linear relationship between the number of chirps made by the striped ground cricket and the air temperature. A least squares fit of some data collected by a biologist gives the model predicted y equals 25.2 plus 3.3x, where x is the number of chirps per minute and y hat, predicted y, is the estimated temperature in degrees Fahrenheit. What is the predicted increase in temperature for an increase of 5 chirps per minute? So here's our equation. But I can also look at this as just change in temperature. That little triangle means change in. So that's fine to look at too. So I'm going to substitute in 5 as the expected change in temperature, change in chirps, and multiply it out, add it in, and we get 41.7. So our answer is we expect an increase in temperature at 41.7 degrees. Okay, personally, I think that I guess you're measuring the chirps per minute, but if we were to look at this in terms of explanatory and response, I'm pretty sure the temperature is changing the chirps per minute rather than the chirps per minute changing the temperature. But I guess if you don't have a thermometer, you could use the vice versa to measure it. But in my opinion, yes, I think in the real world, if I said which one is explanatory, I would say the temperature explains the number of chirps per minute, and I'm very confident in that. Number 10. The first scatter plot shows the lean body mass and metabolic rate for a sample of 5 adults. For each person, the lean body mass is the subject's total weight in kilograms less any weight due to fat. The metabolic rate is the number of calories burned in a 24-hour period. Because a person with no lean body mass should burn no calories, it makes sense to model the relationship with a direct variation function in the form y equals kx. And you physics students are probably going, hey, that looks like a spring constant. Maybe. All right. Models were tried using different values of k. The sum of the squared residuals was calculated for each value of k. Given it is the second scatter plot, this one showing the relationship between the sum of squared residuals and k. Well, according to the scatter plot, what is the ideal value of k to use for predicting metabolic rate? Well, we want to minimize the sum of squared residuals. So the best fit is when the sum of squared residuals is the lowest. And that appears to be that point right there, which means k should be somewhere from 30 to 32. D would be a good choice, 31, all right? So it's lowest when k is between 30 and 32. We'll choose 31. Number 11. We record data on the population of a particular country from 1960 to 2010. A scatter plot reveals a clear curved relationship between population and year. However, a different scatter plot reveals a strong linear relationship between the logarithm base 10 of the population and the year. So we're dealing with a transformation here. The least squares regression line for the transformed data is log of population equals negative 13.5 plus 0.01 times the number of years. Based on this equation, which of the following is the best estimate for the population of the country in the year 2020? So I'm going to go ahead and rewrite the equation right there, make it easy to see. We want to predict for the year 2020. So we substitute that in, and when you multiply that all out, you get 6.7. But that's the log of the population. And to pull that population out of the log, what you want to do is put whatever this base is, and they said base 10. So put a 10 here as a base, and put a 10 there as a base, right? We're ignoring this because we're done with that, right? So you have 10 as the base on both these numbers. They're equal numbers, log of population and 6.7. And the cool thing is population pops out that way. And 10 to the 6.7 is about 5 million. So the correct answer here is C. All right. So when you have these transformations, make sure you get a little comfortable. If you have a log of something, that you put the base down on both sides of the equation, and then that pops the inside here out of the log, and then just use your calculator. Go 10 to the 6.7, either using the caret that points up or the X to the Y button. Number 12, a botanist found a correlation between the length of an aspen leaf and its surface area to be 0.94. Why does a correlation value of 0.94 not necessarily indicate that a linear model is the most appropriate model for the relationship between the length of an aspen leaf and its surface area? Choice A says the value must be exactly 1 or -1 to indicate a linear model is the most appropriate model. All right. No, it doesn't have to be all the way to 1 or -1. 0.94 might be a beautiful linear fit, but how do you know? You got to check the residuals. Check the residuals. If there's no pattern, then linear is great. If there is a pattern, try something else. So not A. B, the value must be 0 to indicate a linear model is the most appropriate. Well, if a value of 0 means there's no linear relationship, there's no correlation, so it's not B. C, a causal relationship should be established first before determining the most important model. Actually, you can have a model between two variables where one of them is not the causal of the other, and it could be there's a confounding variable that's causing both to change in the same way. The model's not about causation, it's just about a linear relationship, all right? D, the value of 0.94 implies that only 88% of the data have a linear relationship. Actually, that 88% of the variation, not the data points of the variation, is explained by the linear model, so it's not D. Even with a correlation value of 0.94, it is possible that the relationship could still be better represented by a nonlinear model. That is correct. You can get a very good correlation even though it is not linear. For example, it's sort of like this. You could probably get a pretty good relationship even though there's sort of a curve on it. So E is the correct answer here. Number 13. The height H and collar size C, both in centimeters, measured from a sample of boys, were used to create the regression line. Predicted collar size equals -94 plus 0.9 times their height in centimeters. This line is used to predict collar size from height, both in centimeters, for boys' shirt collars. Which of the following has no logical interpretation and context? The predicted collar size of a boy with a height of 140 centimeters. Well, assuming 140 centimeters is a reasonable height for a boy, it should be fine, all right? The intercept of the regression line, I think that means the y-intercept, by the way, it's -94 centimeters, and we would have a boy of 0 centimeters tall. Not likely, all right? So it's probably B is our answer. C and D, the H values and C values in the sample, those are actual original values in the sample. They're fine and they don't defy logic. And the slope of the regression line is fine. It explains the expected change in in collar size when the height is increased by 1 centimeter. So go ahead and switch those two. All right. So, although, there you go. Yeah, because we can't really, I have my explanatory and my response variables switch. So that's kind of funny. All right. Number 14. Oh, just to make sure, you know, the answer is B, the intercept of the regression line. And by intercept, we're talking about the y-intercept. 14, a researcher collected data on the age and years and the growth of sea turtles. The following graph is a residual plot of the regression of growth versus age. Does the residual plot support the appropriateness of a linear model? Well, I'm pretty sure I see a pattern right there. There is an obvious pattern in the residuals, so a linear model is not appropriate. In fact, I think a quadratic probably would be great. So no, because the graph displays a U-shaped pattern. Number 15, a family would like to build a linear regression equation to predict the amount of grain harvested per acre of land on their farm. They subdivide their land into several smaller plots of land for testing and would like to select an explanatory variable that they can control. Which of the following is an appropriate explanatory variable that the family could use to create a linear regression equation? Well, the first one, the amount of fertilizer, seems reasonable and controllable. You can control how much fertilizer you put on each plot. Then B, they say the total amount of rainfall. Well, that's, unless you can do a rain dance, you can't really control that, all right? C, the type of crop planted in the plot of the previous year. Well, in theory, you can control the types of crop, even though it's sort of previous year. You could get into an argument about that, but more importantly, the type of crop is not quantitative. We need two quantitative variables for linear regression. D, the average daily temperature at their farm. Again, I don't think they can control the temperature at the farm. And then finally, the variety of grain. Oh, that's not quantitative, so that would be very difficult. So the only one that we can control that is quantitative is the amount of fertilizer applied to each plot of the land. And that is the end of the solutions for your review for the multiple choice section. Good luck on your test.